Okay, so we're doing 4.1. This whole chapter is on what we call congruence. So we are going to be looking at what does it mean to be congruent, and then also how do we show that something's congruent, okay? So that's the whole thing about this chapter. And basically, some of this is kind of pretty evident, but the whole idea of congruence is that they're the same size and the same shape, okay? If two figures are congruent, they're exactly the same size and shape. Okay, so if I draw a right triangle like this, if I draw another one that's exactly like that, and I'm not a good drawer, so I probably can't do it without a ruler, but something like that, those are meant to be congruent, okay? And so that means that this and this, this and this, that and that are all the same, okay? Congruent is not when I draw one smaller. It can't be smaller. Those are going to be similar to each other. They're going to have proportions the same, but they're not exactly the same. Okay? So, congruence is when we're looking for things that are exactly the same size and shape. These can be lines, it can be triangles, it can be angles. There's all sorts of things that you can use to be congruent. So when we're going through this section, we're going to talk about the same size of lines or line segments. You can't really have the same size as lines, but you can have the same size line segments. Okay, so we use this a lot in repeating patterns, okay? We use congruent shapes a lot in decorating. When you look at even just the floor, if you look at all the different tile things or the, whatever they are, they're the same, exactly the same. They may be turned differently, but they're exactly the same. Okay, so if you, it's especially evident when you go into a bathroom or something and they have tile on the floor, and they may have the same pattern throughout. And so that is called congruent. We use congruent shapes that way. So it's really in decorating, in building, we use congruent shapes. Sometimes brick is done in 2 or 3 different sizes, but they just keep repeating the same pattern with those 2 or 3 sizes, and those are congruent shapes. So it's really nice to make different patterns with them. If people quilt, if any of your parents or mother's quilt or your grandma's quilt, they are using congruent shapes in their quilt, okay? So that's what gives the pattern of the quilt. And so congruency is a lot about the same size things, repeating it, okay? We hope when we build, like that one window and that window and that window and that window are congruent. That means they're all the same size. It looks better to us than if we made that one and this one's 5 inches smaller and this one's 7 inches bigger and that one's just a foot by a foot. That would really look weird on our building, okay? And so we use a lot of that when we're going through and making buildings because it looks better to have some balance, some congruency in there, okay? That's why most roofs have a pitch up and a pitch down. They have like a triangle at the end of the roof. That gives you congruency. Some of them sometimes go farther down, but it's usually the same size if you have a peak anywhere on your roof. Okay, so there's a lot of different things that we look at for congruency, and it just, if they aren't congruent, then it bothers our eyes, to be honest. We like repeating patterns, okay, and so it bothers our eyes if things aren't congruent. So today we're going to take line segments. This whole section here is on line segments on a coordinate plane. So a lot of geometry uses a coordinate plane, and the coordinate plane is kind of how we tie it back to algebra, because we're looking at similar things on a coordinate plane as we do in algebra. So what we're going to talk about today is including the distance on a coordinate plane, the distance between 2 points. This is something we have done before. We're going to just go into a little reminder, okay? So first of all, we can use a coordinate plane. A coordinate plane is when we talk about your basic X, Y graph, okay? It's your basic X, Y graph. We can put measurements on our X, Y graph by using equally spaced units on the x-axis and equally spaced units. The best way when we're looking at these in geometry is to use each unit, that's equally spaced. We don't want to jump on one axis. So this is going to go out in the positive direction. This is going to go out positive. This is going to go out negative. And again, we're talking about distance here. It's not, direction is negative. Negative means a direction. And when you're graphing, this means you're going left of the origin. So negative here means the direction of left. Positive here means going to the right of the origin. This is left of the origin. So we're not really, these aren't negative numbers in the sense that they are, they're directional numbers when we use them in geometry. Okay. Going up in the positive, that's going up from origin. If you're going negative, it's going down from the origin. Whoops. Now, when we're doing these, it's probably wise to use graph paper. Okay, so for this class, I did ask you to get some graph paper. So make sure you have some to use because it makes your drawing much, much easier. Okay, it makes everything that you do a lot easier. If you just draw it on your paper, you're not going to get accurate things. So please use graph paper on any of the things that we're using on the coordinate plane. Okay, that makes it easier for all of us. Okay, but we know, why is it called the coordinate plane? Can anybody tell me why it's called the coordinate plane? Is what?
I wouldn't say that.
Was that a smart, nice little comment?
It wasn't anything to do with that.
Oh, it wasn't, okay. Okay, Jake, that's fine.
Is it because there's coordinates on a plane?
What are coordinates?
They're like points at certain places.
Okay, the coordinates are the points. So we use coordinates to find a point. How do I write a coordinate? What does the coordinate stand for?
A number?
What is it, just one number? Think about what
It's two numbers.
It's two numbers, so a coordinate represents a point, but a point has to have two numbers. What are the two numbers that we have to use in a coordinate to indicate a point? Yes.
The X and the Y.
The X and the Y. So it's an X, Y point. What does the X really stand for in the coordinate? Think about this. Think about what these positive negatives, what does the coordinate actually stand for, the X coordinate? Yes.
The distance from left to right from your point of origin.
Yeah, that's correct. The x value is how the distance from the origin, either left if it's negative or right if it's positive. So this is the right, left direction number. The number that you go in right or left. Okay, why did I say number 4? I have no idea where that 4 came from. Number, it's just the number, okay? So what does the y coordinate stand for? Lucas, what does the y coordinate stand for? We're doing what?
Up and down.
We're going up or down direction number. So that's really what it's a placement. It's like GPS. They use GPS in the world now. It's huge. We use it everywhere. That's a global positioning system. It is using points to indicate where you are on the earth. Those are by latitudes and longitudes. So that's what it's using. Latitudes go around the earth this way. So it's like your X. Okay, longitudes go up and down. Okay, and so that is your up and down direction. So it's all from the equator, and I think it's the international date line is the place where it goes from. I'm not positive on that. I know the equator is where the 0 is for north and south, or up and down. I think it's the international date line where it comes from, but I might, is that? Yeah, okay. So it's at the international date line. That's where the 0, so that is our intersection or origin, is where the equator passes the international date line. Okay, and so that's where the axis would be. And then where you're placed on the earth, it's a little different because it's not a plane. But we really kind of make it a plane, the Earth's surface a plane, and that way we can plot on where these different places are. So we take the Earth and kind of make it, lay it out, okay? So we can find out where you're at based on how far you are, left or right. It's probably always going positive if I think about it, it's probably always positive. But it tells you where you are at, how far you are from the international date line this way, and how far up you are from the equator, or how far down you are, okay? So it gives you both of those, okay? So that's what our GPS system is. It's actually using a coordinate plane, to describe your location on the earth, okay? We have a different set of axes, but that's just, we have to know where the center is or where the origin is. You can't do a global positioning system with no origin, because it would make no sense. You have to know where you're starting from and how far you're going to the left and right, or how far you're going up and down. And so that is what we are looking at with GPS. So you guys have access to that all the time, but you might not really think about what that means, okay? We know our computer or our phones know how to read that. We don't always know how to read it, but it is good if you ever go hiking and you get lost or something. GPS usually is available. You can usually get GPS, and so then you can find out kind of where you're at and where you want to head towards. And that should give you an idea. Do I need to go north, south, east, west? Trying to depend where I'm going, okay? Okay, so when we put a point on here, so let's say I put the point 2,5 on here, okay? That's 2 over, so this is a point 2,5. And then over here I put a point 7,1, okay? And on a coordinate graph, we are actually going to look for the distance between the 2 points. This is something you can actually do with GPS coordinates. You can actually find the distance between 2 points if you have their GPS. Might not be pretty, because they're not given to you as really beautiful, like even numbers, like I'm giving them to you, but you can do that, okay? One of the things that we use to find distance is we realize we can go down here and over here, and we can make a right triangle. So what we do is, if we want to find distance, we make the right triangle that goes with that distance. So we make the distance the hypotenuse. We make the distance the hypotenuse of our right triangle, okay? And so it's really easy. You can figure out, okay, 5 down to 1. How far did I go? I went 4 steps, right? From 5 down to 1. One way of finding that is 5 minus 1. So it's the x value or the y value of 2 minus the y value of 1. That's a lot of times how it's written. You just decide which point is 1 and which point is 2. But you have to be consistent when you do this, okay? So I can find that distance, that's 4, okay? And I'm going to square that because in the formula for a right triangle, we take the legs and we square them to find the hypotenuse, okay? I want to find the distance from 2 to 7, but again, now we're looking at, okay, I need to stick, I want 5 to 1. I'm just going to show you, this doesn't necessarily change anything. I need to go from 2 to 7. Now, if I subtract 2 to 7, so that's x2 minus x1. What I'm doing here is I'm using the same points. So I'm calling this one point 2, and this one is point 1. So if you're looking at it, the y value in point 2 minus the y value in point 1. I should be consistent then to go the x value in point 2 minus the y value, or x value in point 2. Okay, we're going to square that. So what we get though is 2 minus 7, which is negative 5 squared. Notice what happens when I square it.
-5.
If I take negative, yeah, because remember, 2 minus 7 is negative 5. I'm showing it with the formula, okay? So that's how you do it with the formula. I think it's much easier just to count, okay? And you're going to get 5. But negative 5 squared and 5 squared, same answer? Yeah.
Will homework ask for the formula?
I hope not, because I'm going to tell you that drawing it's much easier to find than, and counting is much easier to find than using and memorizing a formula, okay? I don't like to memorize formulas. I like to know why it works, and then I can easily find it my own way. So in here, this is going to equal c squared, or it's going to equal the distance squared. There's our distance, because c is the actual distance between the points if I were going as a bird flies. Okay, so from here to here, straight across is the distance, which is the hypotenuse, which is the c squared, which we can call distance squared. Okay, so you're going to see it as distance squared in your book. Okay, so now what we get is d squared is equal to 16 plus 25. Okay, because 4 squared and negative 5 squared. D squared is equal to, what is that, 41? Is that right? 41? Yeah, that's right. Okay. What is my distance going to be equal to? What do I do now to find that?
The square root of 40?
Yeah, you take the square root of 41. What you're really doing is taking the square root of this and the square root of that. This is going to be just d, because if I take the square root of d squared, it just becomes d. They cancel one another. And do I know what the square root of 41 is? What is 6 times 6? 36. What is 7 times 7?
49.
Oh, so where is the square root of 41 going to fall?
Between 6 and 7.
In between 6 and 7. Okay? We can almost guess these. Okay? Because if we look at it, we have some perfect squares. 6 squared is 36. 7 squared is 49. Well, 41 falls pretty well in the center of that. So I'm going to say it might be about 6.5. Now, pull out your calculator and let's see how close we got. Okay. I'm just saying you should be able to kind of guess what the answer is going to be. And then when your calculator gives you an answer, you should be able to say, oh yeah, that is close to that. Because if I get something like 77, we know that's not close to 6.5, and that shouldn't be a wrong number. Okay.
About 46.5 squared.
No, I'm asking, take the square root of 41 and give me what you get. What is the square root of 41? Anybody get it?
6.4.
Oh, it's 6.4. Does it round at all?
Uh,
What's the next number?
0.
Oh, okay, so it doesn't. I was a little off. Now, if you look at this answer in your calculator, does it stop? Does it stop on your calculator? Does it have more decimals besides 6.40? Does it have more
Yeah.
numbers following that? Do you ever see any repetition? No. Square root numbers like this, really, they go on, they're like pi. A square root that is not exactly 6 or 7, all square roots are like pi. They never repeat. They never stop. They're called irrational numbers. Okay? Because pi is an example of that's our famous example of the irrational numbers, because it goes on forever and never stops. We all know that. Okay, we've heard that over and over. What we don't know is that every square root of a number that's not a perfect square, okay, that's not exact like that, is also irrational. It also goes on forever and ever and ever, and doesn't ever end or start repeating. Okay, so that's what's called an irrational number. But because I looked at this, I knew it was going to be close to 6.5, then I could make sense of what my calculator gave me and say, that's a correct answer, and I'm not just lost at what the answer would be. Okay, so you should always be able to kind of gauge what is the answer approximately. Well, I know it's going to be between 6 and 7 because 41 comes between 36 and 49. So it has to be between those two. Okay, so that's what we're working on here, is just coming up with how long are things, how the measurements of things when they're in a coordinate graph. Okay, now they're going to give you this formula. I will just show you the formula they actually use, because you should be able to maybe recognize it, because a lot of math books will give it to you. It's like this. Okay, that's the formula. That's all of the work that you have to do to get it. And you can plug and play with that formula if you have that formula, but you really need to know what all the values stand for. And so in this, you have 2 points. If I call it point 2 or 1, then it's x1 and y1. point 2 is called x2 and y2. That's what those stand for, okay? So you need to kind of know what those mean. It means you're supposed to be consistent, but I'll tell you, when you do it, it's probably not going to make a difference because you're going to square the answer anyway, okay? Now, my way of doing these problems, okay, let's use one that has some negatives in it. So we're going to put a point down here that's at 2, -2, and we'll go -3. -3, so that's our point right there. And I go 1, 2, 3, 1, 2, 3. I'm going to put the other point right here at 1, 2. Okay, so here's my, I can either go like this to make my right triangle, like that, or I could go up and make the other right triangle. It doesn't matter. Okay, just make the right triangle. So I have this point, that's where I'm starting. I'm looking for this distance between here, so that hypotenuse length, and I have these two sides. Okay, so if I go from 2 down to -2, what is the length of this side?
4.
It's 4. Can you see that there? 1, 2, 3, 4. I went from 2 down to -2, that's 4. Okay? If you subtracted them, let's see what happens. I could take it either way. It would be 2, oh, that's not gonna right. It could be 2 minus the -2 squared, or it could be a -2 minus 2, because I have to subtract them, squared. Well, this is 4 squared. This is -4 squared. Do you see I get the same answer? So if I were using it here, I could use either point and I would get the same answer. But to me, if I have little things, I can count and figure out what the length of that is. That's 4. Okay? How far do I have to go from this way to this way? Well, I went from -2 or -3. -3, sorry, not a good drawn graph. -3 up to +1. So I went 1, 2, 3, 4, that direction also. Okay, so this side is 4. So I have that side is 4, this side is 4. I'm looking for the hypotenuse. So I just go back to my old Pythagorean theorem. A squared plus B squared equals C squared, because I don't want to have to remember that junk. So I just want to remember what are my lengths? I can count my lengths because they're usually on the horizontal and the vertical. And so you can just do it. A is 4, B is 4, and I'm looking for C squared. So I have 16 plus 16 equals C squared. 32 equals C squared. The square root of 32 equals C. Again, that's not going to be perfect. What number is the square root of 32 going to be in between? Or what number will it be around? Luke. Where's Luke? He's not here. Blake,
What was the question?
what is the square root of 32? What numbers would it fall between? Don't use your calculator, Lucas. Try to figure out.
Square root of 32.
Yeah. This is
So,
good to remind your
5
perfect.
times 5 is 25.
That's correct.
6 times 6 is 36.
Okay.
So it would be like a 5.5.
Sure. Okay, somewhere in there. 6 squared is 36. 32 is somewhere in between there. It might be 6.5, 6.6, somewhere in there. Okay. You guys are lucky. You guys get calculators. When I was in school, we had to look up square roots on a square root table. So we had to have a good idea of where to go to get it. And so we had to actually look them up on a table to find them. They were all calculated out, but instead of doing it over and over again, we have to guess and try to figure out what it is. We had a table that we could look up. Okay, you guys have a calculator you can use. The reason I tell you about this though is it's between 5 and 6. It's because I want you to know that that answer you get is reasonable. If I come up with an answer that says 75, means I probably did something wrong in my calculator. Okay? You can't always predict, like, don't give me the answer, that's what my calculator said. Because you should kind of have an idea of what the answer is going to be. What should it look like? Okay, and so this is where you can kind of guess. You might not get exact, but you can give it a good guess. Okay, so that's something to look at. So my theory is, remember the Pythagorean theorem. Make your right triangle on there. Count the sizes or the lengths, and then you can find the distance between those 2 points. Okay, so if I had another line on there that when I did the calculations, it came up with the square root of 32 also, what would you say about those line segments? So if I had another line, say it goes from here. Okay, we're moving it. Okay, that's correct. And I'm going 4 and 4. Say I had that line segment. And if I calculate that, what do you think I'm going to get?
Is it congruent?
It's congruent. Yeah, these are going to be congruent. Because if I calculate this new line, I'm going to write the triangle the opposite way so you kind of see that. Here's my triangle. Okay. I'm going from 0 to 4, so that's 4. I'm going from -3 to -1, that's 4. Do you notice how that's the same as this triangle? So my length here is going to be the same thing. So if they are the same length and they're both line segments, they are the same size, they are the same shape, they're both line segments. Okay, and so that would be our distance. Now, if I had something that if I went up and down and that totaled 4 altogether, those are not congruent because that's not just one single line shape. Okay, one line segment. Does that kind of make sense? In there? Okay, so that's basically what they're looking at in here. They're using that formula. Like I said, if you're more comfortable with just using the Pythagorean theorem, that's easier to use in my estimation. Okay, so you can find out what they are. You can always make a graph of whatever points you have, and then you can check what are the lengths of the sides. Okay, so we're going to 4.2. This one is all about just really finding distances. They are congruent if they're both lines and line segments and their distance is the same. Okay. So really here we just talked a lot about the distances. Okay, 4.2 now. This section is about polygons and congruence. So now we're kind of going into something different, but again, it's on congruence. This whole chapter 4 is on congruence. That's what we're looking at, okay? So this one is titled Polygons and Congruence. Just as a reminder, what is a polygon? Yes.
A shape with more than 3 sides? Or 3 or more sides?
3 or more sides, yes. It has to have 3 or more sides. What else does it have to have?
It's 2-dimensional.
It's two-dimensional. How else would you describe it? You know what else polygon has to have?
It's on the same plane.
They're all coplanar, yes. Coplanar. That actually is kind of described by two-dimensional because two-dimensional is on a plane. Okay, but they are coplanar. What else do you know about them?
There can't be an open end.
Yeah, we can't have any open side. No open side. It has to be what's called a closed figure. Now, so when we talk about the sides, what are the sides? Are they circles? Are they squiggly lines? Are they waves?
Line
Yes.
segments.
They're line segments. A polygon has to have a line segment as a side. Okay, so this drawing here is not a polygon because that is not a straight line on that third side. All lines have to be line segments. They can't be curved lines, they have to be straight lines. Okay. How do we name polygons? I should say, how do we know if it's a triangle, a quadrilateral, a pentagon?
Based on how many sides it has.
Yeah, so the basic shape, the shape is determined, the shape name I should say, the shape name is determined by a number of sides. So, when we are looking at, and if you look on the top of page 140, why don't you open up to page 140 in your book? I just want you to see. Look up at the top there are two that are not polygons, okay? There's ABCD at the top left-hand corner. Why is ABCD not a polygon? Lene, why is ABCD not a polygon? It's not a closed figure. It does not close. So if you're looking up, it's right on the top left-hand corner. We're looking at those two. Then you have FGIHE, FGIHE. So why is that not a polygon, Paxton?
The lines intersect.
The lines intersect. You cannot have intersecting lines. So you might want to look at that too. No open sides and no intersecting line segments. Except at endpoints. So they don't intersect anywhere, but they can intersect, which they have to intersect to make it closed at an endpoint. So they intersect only at endpoints is another way of saying that. So basically knowing that you can't have a figure that's like this to make a polygon or something like this. Those are not polygons just because they don't fit our definition. There's an area inside that's closed. This is two areas. It's only one single area inside of a polygon. Okay? So when we name polygons, we talked about this before, but it's probably been a while. So when we name a polygon, the most commonly named polygon is the triangle. Okay, So when we name it, we have this triangle. Then you put the endpoints on your triangle, and it doesn't matter how you name the triangle, but you need to name it in order. Like if you start at A, you go clockwise. If you start at C, you go clockwise. Okay? So you just have to go in order when you're doing it. So you name it with a little triangle sign. That means it's a triangle, means it's a polygon. And then you put, and I always usually start with A because it's alphabetical, but you do not have to do it alphabetical. That's a triangle there. I could also name it BCA, very similar. Or I could name it CAB. I wanted to call it cab. Okay. So I can name those, all three of those are naming that same polygon. Okay. The reason that's important is when we start talking about congruence, we have to have corresponding angles matched when you name the triangles that are congruent. Okay. So, basically, if I have congruent polygons, what do you think that means? If two polygons are congruent, what does that mean?
They're the exact same.
They're the exact same. They're not actually the exact same because they may have two different names, but they're the same size and shape. So that means they have the same, all the sides are the same side lengths, same angle measures, so what that gives us is the same size and shape. Okay. So let's kind of just get an idea. I'm going to show you some notation that we're going to see. Some of this is just so you can be able to read it. It's really going over notation and words right now. Okay. So let's say we have this triangle. Okay, and then we have this triangle. Okay, because I don't draw well, I'm going to tell you that this side length is the same as that. So when we're marking same sizes or congruency of sides, a dash, 2 dashes, or 3 dashes, you can actually go to 4 dashes if you want, means, so if it's on both, it means the two sides are congruent. So in this case, this side and that side are the same, okay? I also want to tell you, because I can't draw perfectly, I'm going to tell you that this side and this side, so see they match, they have the same markings, so they are congruent, okay? And I'm also going to tell you that this and this one are the same, so notice the ones mark, 1 slash on each one matches, the 2 slash match, and the 3 match. Yes.
So would you keep going with Roman numerals and go to V with 5 sides? Or would you just do it up?
We don't usually go up. We do most of this on triangles. You'll just find that most of our work is done on triangles in trig. We don't go up to the bigger polygons. So yeah, we might use squares, and squares you would use all
Right.
4. Yeah. Basically, yeah, you could go to Roman numerals and that would be fine because as long as both of them are using the same symbol,
Right.
but it's usually just the kind of the lines that indicates congruence in line segments. Okay, so that's line segments. How you mark line segments are the same. okay? Usually with angles, it's very similar, but it's different, okay? One single little curved line means they're congruent. So if they have the same number of curved lines, so a curved line, 2 curved lines, or 3 curved lines means the angles. And again, you could use 4, okay? A lot of times when we get above 4, that start to be very cumbersome to write. A lot of times we will number the angles instead and say those are congruent, that angle 1 and angle 2 have the same measure, okay? So sometimes we'll number them. So like if I put this and this, 2 lines like that, that means those 2 are the same. If I put 3 here, that means those 2 are the same, okay? So are these 2 shapes congruent?
Yes.
Yes. Now, it may not look like in my pictures that they're the same shape, but we have to go by the drawings because the drawings are what we mark up there. That's more accurate, okay? Because you noticed I didn't use rulers or anything to make sure that those were identical, okay? So, when we're naming these, this is the important part. D, E, F, okay? If you look at these, corresponding parts must be named in the same order as the corresponding parts on the other triangle. What do I mean by that? Okay, so if I'm looking just at the angles, when I write the names of the triangle, this triangle up here, I'm going to name it A, B, no, I'm going to name it C. Now, I'll name it ABC. A, B, C. So that's that triangle. I have to name this one so that whatever is congruent to angle A is congruent or is written first. So what is the angle that's congruent to angle A? What's the angle in the second one that's congruent to angle A? D. So when I write these, the D has to be paired because those are the congruent angles. They match each other. They're the same size. So it's very important how you write the triangle, okay? Next, I have B. So I need to write whatever is B, the same size as B in my next one. Jake, what would that be? Which one's the same as B?
F.
F. So I'm going to write it as DF. Now it should be pretty easy to figure out what's next because we have a triangle with 3 points, so E goes, but we can check. They all are the same size. A is the same as D, B is the same as F, C is the same as E. Those are called corresponding parts. So they are line segments or angles that have the same measure in both polygons. So you always want to match up the 2 that have the same measure when you're listing the names of the triangles. Okay, so when we go to say that they're congruent, I have to say that triangle ABC is congruent to triangle DFE because these are corresponding parts. A and D are the same, B and F are the same, C and E are the same. So you have to write it that way so that you know that the corresponding parts here, just by that statement, I can tell you that A is equal to D. I can tell that B is equal to F and C is equal to E. I can also tell you that AB is the same as DF as far as a line segment. I can tell you that BC is the same as FE as a line segment. And you can also see that AC and DE are the same as a line segment because they're in the same corresponding part of the polygon. Okay, so that's what a corresponding part is. Okay, so that's basically everything that's in 4.1 and 4.2. We are now going to take a break. We'll come back and work on some activities. Let's see.
Wait.